Welcome to the Deep Dive, where we unpack complex information to help you get truly well-informed quickly.
Yeah.
Imagine this. You're, say, a sophisticated AI, trained perfectly on clear, sunny images for a self-driving car, but then, bam, you hit a dense snowstorm.
Yeah, or maybe you're a medical AI, right? Tuned on perfect lab scans, and suddenly you get this grainy image from an older machine.
Exactly. That gap, that difference between the training data and the real world, that's called distribution shift. And it's a huge challenge for AI.
A really fundamental one.
So today we're diving deep into a fascinating paper that tackles this head-on. It's called Test Time Training with Self-Supervision for Generalization Under Distribution Shifts by Sun and colleagues. You've given us the work, study guides, briefings, quizzes, the paper itself. Our job is to boil down the core ideas, the clever mechanics, and the implications without making your head spin.
Absolutely. At its heart, this paper addresses how machine learning models cope when the data they see out in the wild isn't quite like their training data. And this distribution shift, it happens way more often than you might think, and it can really trip up even very advanced models.
Okay, let's break this down. We're saying AI models can get thrown off by seemingly small differences between their neat training world and the messy real world. What's the basic problem they're trying to solve?
Well, the core issue is that standard supervised learning models, they're just notoriously weak at generalizing when these shifts happen. Think about that cat and dog model trained in perfect studio lighting. You put it out on a dim, rainy street. Completely different distribution. Performance drops.
Right, and usually people try things like adversarial robustness or domain adaptation, trying to guess these shifts during training, like trying to prepare for the storm before it arrives.
Exactly, you try to anticipate. But test time training, or TTT, flips that script. It's a pretty novel idea. Instead of guessing all possible future problems during training, TTT says, let's learn from the shifts when they happen at test time. It sees an unlabeled test sample as a kind of hint about the current conditions.
Okay, now this part really caught my eye, the variable decision boundary.
Yeah.
What does that actually mean for the model itself? How does it work?
It means the model's parameters, think of them as its internal rules or settings, are actually allowed to adjust just a little bit for each specific test sample it sees before it makes a prediction. That's a huge shift from traditional models where the rules are locked in after training.
So it's not sticking to a fixed theory.
Right. It's more like a detective who subtly reevaluates the case based on every new clue, instead of being locked into one initial idea. The model fine-tunes its understanding based on the data it's actively processing.
That makes a lot more sense for the real world. It's like the model is always learning, always adjusting slightly.
Exactly. So, okay, how does TTT actually pull off this on-the-fly adaptation? The key ingredient is something called self-supervised learning. This involves an auxiliary task, a secondary job for the model, where it generates its own labels from the unlabeled input data. The main example in the paper is the rotation prediction task.
Ah, right, where you take an image, rotate it randomly like 0, 90, 180, or 270 degrees, and the model has to predict the rotation angle.
Precisely. It's a really clever way to get a learning signal without needing any human labels like cat or dog.
Yeah.
It forces the model to learn about the image's structure.
Ingenious. So how does the model juggle this self-supervision with its main job?
They use a specific architecture, a Y structure. Imagine a base, a shared feature extractor, like the trunk of a Y. This part processes the input image. Then it branches into two heads. One head tackles the main task, say, classifying the object. The other head handles the self-supervised task, like predicting that rotation angle.
So one network, two jobs, sharing the initial processing.
That's the idea. And during the initial training, it learns both tasks together, using the same labeled data. The losses from both heads are combined. This trains the shared trunk to learn features useful for both recognizing objects and understanding things like rotation. And crucially, they found group normalization, GN, works much better here than batch normalization, BN.
Why is that?
Well, BN needs large batches of data to work well, but at test time, TTT is often just looking at variations of one image. BN kind of falls apart there. GN doesn't depend on the batch size, so it's stable even when adapting to single samples.
Got it. So group normalization is key. Then test time comes. A new unlabeled image arrives. What happens?
Okay, this is the standard TTT process. The image comes in. The parameters in that shared trunk are then fine-tuned. How? By minimizing the loss on the self-supervised task, like the rotation prediction error, just for that single image. They usually do maybe 10 quick gradient steps, small adjustments to the model settings based only on this one image.
A quick calibration, personalized for that image.
Exactly. Only then does the model make its main prediction using these slightly adjusted parameters. And then, importantly, for the next new image, it resets those parameters back to the original trained state before adapting again.
Okay, but what about video? Like our self-driving car example. Resetting for every frame sounds inefficient.
Good point. And that's where online test time training comes in. It's designed for sequential data like video. Instead of resetting completely, the parameters updated from the previous frame are used as the starting point for adapting to the current frame.
Ah, so it builds on the previous adaptation.
Right. It allows the model to track gradual changes in, say, lighting or weather across frames. It leverages the recent past. As the paper says, prediction is rarely a single event. And for this online version, they often just take one gradient step per frame. Much faster.
Okay, the method sounds really elegant. But does it actually work? How do they test its performance?
They really threw the kitchen sink at it, using standard benchmarks designed to test robustness against these distribution shifts. First up, corrupted images. They use datasets like CFAR10C and ImageNet-C. These have images with 15 different types of corruption noise, blur, weather effects like snow and fog, digital artifacts like pixelation.
So deliberately messing up clean images to see how the model copes.
Exactly. Things that happen in the real world. Then they used video frames with VideoRobust. This checks how well models trained on static images handle the natural shifts in video motion, viewpoint changes, lighting variations.
Makes sense. Video is dynamic.
And finally, they used a tough one, CFAR 10.1. This dataset has shapes that are apparently almost unnoticeable to humans, but still cause big performance drops in standard models. A real stress test for subtle shifts.
Oh, okay. That covers a lot of ground. So the results, did TTT actually make a difference?
Oh, absolutely. The results were quite impressive. First, significant improvement. Both the standard and the online versions of TTT substantially boosted performance across all these different types of distribution shifts compared to the baseline models.
Better handling of corrupted data, video, subtle shifts. Check. But what about performance on the original clean data? Sometimes robustness methods hurt that.
That's the most striking part. No trade-off. This is huge. TTT either maintained or even slightly improved performance on the original uncorrupted test data.
Wait, really? So it gets better at handling the messy stuff without getting worse on the clean stuff?
Exactly. On CFAR 10, for instance, the error on clean data actually decreased slightly with TTT. Most robustness techniques force you to choose. Better on noise, worse on clean, or vice versa. TTT seems to avoid that compromise, which is a massive win.
That is huge. What about the online TTT for video-like data?
Online TTT often did even better, particularly when the distribution shifts were gradual, like changing weather in a video. It adapted more smoothly. It's effectively learning continuously from the test data stream without needing labels. And get this, TTT Online frequently outperformed a method called unsupervised domain adaptation by self-supervision, or UDA-SS.
Okay. Why is that surprising?
Because UDA-SS methods typically get to see the entire unlabeled test dataset during their training or adaptation phase. TTT Online only sees one sample at a time, sequentially.
Whoa. So adapting sample by sample in the moment was actually better than seeing the whole future dataset beforehand.
It suggests TTT Online's ability to adapt to the current conditions, maybe by selectively forgetting parts of the original training distribution that aren't relevant anymore, is really powerful for handling evolving data streams. It's truly adaptive.
That's fascinating. Did they find any cases where TTT didn't work as well? You mentioned the self-supervised task earlier.
Yes, good point. They did find that the quality of the self-supervised task matters. For example, with the rotation task, if you have images like airplanes against a uniform sky, predicting rotation is kind of meaningless, right?
Yeah, a rotated plane might look almost the same if the background is just blue.
Exactly. In those cases where the auxiliary task didn't provide a strong learning signal, TTT's benefits were limited. So it highlights that you need a meaningful self-supervised task that forces the model to learn useful features relevant to potential shifts.
Okay, so it works really well empirically, provided the setup is right.
Right.
Is there a deeper theoretical understanding of why it works?
Yes, they delve into that too. The paper offers a key theoretical insight, particularly for simpler convex models, but it seems to hold more generally. It hinges on something called positive gradient correlation.
Positive gradient correlation. What does that mean in, like, plain English?
Basically, it means that the adjustments the model needs to make for the main task, like classifying the object, should be somewhat aligned with the adjustments needed for the self-supervised task, like predicting rotation. If fixing an error in rotation prediction naturally pushes the model's parameters in a direction that also helps fix the classification error, then optimizing the self-supervised task at test time will inherently benefit the main task.
Ah, I see. So the two tasks need to be related in a way that improving one helps the other, at least in terms of the direction the model needs to learn.
Precisely. If the gradients, the directions for improvement for both tasks point in roughly the same direction, TTT works well. They even proved a theorem for simple cases. Positive gradient correlation means one TTT step reduces the main task loss.
Okay, theorems are nice for simple models, but did this correlation idea hold up for the big, complex deep learning models they actually used?
That's the important validation. Yes, they empirically checked this for their deep learning experiments and found a strong positive correlation between this gradient alignment and the actual performance improvement they observed. So the theory seems to match the practice even in complex networks.
That's reassuring. So, stepping back a bit, where does TTT fit in the grand scheme of machine learning research? It feels like it connects a few different areas.
It definitely does. It builds on concepts like learning on test instances, which had explored adapting models to individual inputs before, maybe for things like image enhancement. And obviously, it heavily relies on self-supervised learning for that auxiliary task mechanism.
How does it stack up against, say, adversarial robustness methods? People talk about those a lot for AI safety.
It's quite different. Adversarial methods focus on defending against specific, often tiny, malicious changes designed to fool the model. TTT isn't about malice, it's about adapting to natural shifts in the data distribution. Also, adversarial training often makes the model worse on clean data, that trade-off we mentioned. TTT avoids that and adapts to any kind of shift, not just predefined adversarial attacks. It's more general for real-world robustness.
Okay, and compared to unsupervised domain adaptation, UDA, you mentioned it earlier.
Right. UDA also uses unlabeled target data, but typically assumes you have a large batch, maybe the whole target data set, available during training or a distinct adaptation phase. TTT is more like one sample UDA on the fly. It adapts sample by sample at test time without needing the full target data set up front. This makes it way more flexible for scenarios where the data comes in a stream or the distribution keeps changing. It also relates to ideas in domain generalization and continual learning, offering a unique post-deployment adaptation angle.
So, thinking bigger picture, what are the implications here? This sounds like it could really change how we develop and deploy AI.
It points towards a pretty fundamental shift, yeah. The authors talk about potentially abandoning the self-imposed constraint of a fixed decision boundary for testing, maybe even blurring the lines between training and testing altogether. They envision a future where much of the learning happens after a model is deployed, which, if you think about it, is much closer to how we, as biological systems, learn continuously adapting to our environment.
Wow. AI that doesn't just get deployed, but continues to learn and refine itself out in the real world. That's a powerful vision. What's next for TTT research?
The paper lays out a few clear paths. One is just broader applications trying TTT for tasks beyond classification, like segmentation or detection, and in other domains like speech or language processing. Another is leveraging domain expertise. If you know something specific about the potential shifts in your application, you could design even smarter, more targeted self-supervised tasks to boost TTT's effectiveness.
Makes sense. And using TTT itself as a research tool.
Yeah, they suggest using TTT as a new benchmark to evaluate how good different self-supervised tasks really are at capturing generalizable knowledge. And finally, a practical challenge: computational efficiency. TTT adds computation at test time, so finding ways to make it faster, maybe fewer gradient steps, or only applying TTT when a shift is detected using some kind of threshold is important for real-world use.
This has been fascinating. This deep dive into test time training really shows a path towards AI that's much more resilient, much more adaptable to the messy, unpredictable real world. It's not just about making AI smarter in the lab, but making it capable of continuous learning and self-improvement once it's out there.
Absolutely. That core idea, a model that self-corrects and adapts to its environment moment by moment without needing constant human intervention or retraining, feels like a really significant step towards AI we can truly rely on in dynamic situations.
And it definitely challenges the traditional split between training a model and then just testing or deploying it. Maybe learning should never really stop. So as you go about your day, think about those shifts, the changing light, the background noise, the different camera angles. Consider how an AI sees that world. How might this TTT philosophy, this idea of on-the-fly adaptation, change how we build the AI systems we increasingly depend on? Thank you for joining us on the deep dive. We hope you feel a bit more informed and maybe quite a bit more curious. Until next time.